I think I got everybody's name. Just make sure that I did before you leave. I'll stand by the door. I'm going to start with question 20 on spring 24. Address that. Okay, this is a problem that we've worked before, but I think the question was really about if I have a total internal reflection, do I have to move from high to low or low to high? Total internal reflection only occurs when you move from a high index of refraction to a low index of refraction. The reason for that is that as I have total internal reflection, I have a light ray that comes in. It's going to bend back into the medium. And in order for it to bend back into the medium, it has to bend away from the normal. Right? Because if the light ray bent towards the normal, it would never come back into the original medium. So instead, it bends away from the normal, and it'll bend in that direction. Now that's the minimum angle required for total internal reflection. If this angle gets bigger and bigger, then this ray actually will bend back down into the medium like that. But we do consider this at an angle of 90 degrees to still be in that medium M1. So total internal reflection only occurs when you're moving from a high index to a low index, not when you move from a low to a high index. Okay? When you're moving from a high index of refraction to a low index of refraction. So, in this case, it worked out that we were able to find the angle theta 1, but if this was a lower index, then it wouldn't have worked out. Like you would have gotten an error in your calculator. I really encourage you with these problems, if you don't have a picture, to draw a picture and then read the words in the problem and translate it into a picture. Okay? Like if it says the ray of light is traveling through water, then you draw water and write the n value, and then it's traveling into air, then you draw air and you write the n value. I don't think I give you the index of refraction of air, but of course you know the index of refraction of air. 1. All right, we're just going to treat it as 1. It's a little bit more than 1, but we'll treat it as 1. Okay, we did these free response in class. Do y'all want to do those again, or are there other particular questions? Yeah, Kyler? Okay, shoot.
Number 2 was
Okay.
it's really just a percent.
Yeah, so when I made your free response, I cut and paste, or I copied and pasted spring 24. So your free response will look exactly like that. No percentages, but the different thing is I'm not going to give you the time. I'm going to ask you for the time when I reach a certain charge, voltage, or current. Okay? Do I need to do that then?
Oh, just a
No, okay. Alyssa?
Okay, so on spring 21, it's the response of reflection.
Yeah, it's really
On
similar.
number 3, instead of using N3 and 2.
Okay, maybe I made a mistake. Is that this one right here? Spring 21, right? Number 3?
Like I got 57 degrees on the
Okay, let's just do it. We can do the whole thing. So as I move from the low to high, I'm going to move towards the normal. And then as I move from high index to low index, I'm going to move away from the normal. And by the way, also, since this is a lower index than here, I know that this angle must be greater than 50 degrees, right? You don't have to write that, but it helps me to think about if I'm going to get the answer right or not. And then to do part B, I say 1.2 sine of 50 is equal to 1.1 sine of theta 3. I'm not sure what I did. I might have had a mistake in that video. I know that y'all think I never make mistakes, but sometimes I do, actually. Divided by 1.1, and then the inverse sine of 0.83. I get 56.7 or 57 degrees, which jives with what I think it should be. It should be something bigger than 50 degrees. So I'm pretty sure, I'm confident I got that right at this point. Does that answer your question? All right. What else? Yeah.
Can you start on number, there's a number 4 on this one?
Yep.
Will we have an electron or a proton?
That's a good question. I mean, I know, but it's, if you have, there is at least, well, I don't remember honestly, but there is, I'm pretty sure there was at least one question where you had an electron. I don't remember on the free response,
Okay.
but you know,
If we do it.
if it says electron, it's an electron.
Okay.
Yeah. So the difference, what does it do? It really just changes the direction. Everything's the same because the magnitude of the charge is the same. It's just when you get down to part B, the direction, you'll take the opposite of what you find if it was a proton.
So A doesn't do the opposite.
No, because A is only the magnitude of the magnetic field due to the wire. That doesn't affect the electron doesn't affect that. I just want to know what is the magnetic field at this point. B asked me what is the magnitude of the force and the direction. The magnitude will be the same, but the direction will be opposite.
Okay.
Look, when you see electron or negative particle, just put a big circle around it, okay, and then remind yourself to come back to it. Is that clear? Okay. Then spring number 16 on 23. Okay, so we've done these before, where I have a particle that's moving through a magnetic field, and there's also an electric field. I need to calculate both of those. Let's just go ahead and calculate the magnitudes of them both. No, we'll do the directions first. So first of all, the direction of the magnetic force, the velocity is up, the magnetic field is into the page, so the magnetic force is to the left. FB is to the left. Then the electric force, there is an electric field that is moving in that direction. So the electric force, oh yeah. I never make mistakes. The magnetic force is in that direction. Okay? So I had my finger pointed the wrong direction. I had it like this. The magnetic force is in that direction. The electric force is also in that direction. Remember, the electric force is in the same direction as the electric field for positive particles. For negative particles, it's the opposite direction. Okay? Then I know both of these are in the same direction, so now I need to determine the magnitude of each force. The magnetic force, FB, is just QVB. That's going to be 2, this is Q, this is V, this is B, 2 times 4 times 3. That's 8 times 3, 24 newtons. The electric force, this is on your equation sheet. You'll have the full equation sheet. The electric force is Q times V. That's 2 times 4. That's equal to 8 newtons. And so I have 24 plus 8, because they're in the same direction, is equal to 32. Notice that if I had them in the wrong direction like I had done previously, I would have gotten 24 minus 8, which would have been 16. So that would have been wrong, obviously. And then if I'd gotten it where they were like this, where, say, 24 is up and 8 is to the right, and there is a problem like that in your exams, in past exams, then the answer would be the square root of 24 squared plus 8 squared, which I think that's 25, if I'm not mistaken. I'm pretty sure that answer is on there somewhere. Yeah, that's 25. All right, so if they're in the same direction, add them. If they're in opposite direction, subtract them. And if they're perpendicular, you add them like vectors. So I do the square root of the sum of the squares. Okay, Danny? There are other practice problems like that on the past exams. That's one of the more difficult problems because it requires you to remember the electric force. Okay? What else, y'all? Yeah, Mallory? Spring 2111. All right, this is spring 21. Okay, we've done a few of these, and I would expect to see something like this. I'm pretty sure. Honestly, I read the exam a week ago, so I don't really remember exactly what's on it, but this is important. So let's do this up here first, just so I have more space. Imagine I have a wire like this. The magnetic field, I have my thumb go into the page, and so it's going to be clockwise. So the magnetic field goes around in a circle like that. So what I like to do is I like to draw a line that's radial, like this, and the vector that is tangent to that circle is perpendicular to that radial line. So at point P, the magnetic field due to that wire into the page is going to be in this direction. And then for the other one, I can draw a radial line. See, it's out of the page, so that vector is going to be in that direction. Then the resultant of those two vectors is going to be in that direction. So D is the right answer. Let me step through what I just did there. So here, the current is going into the page, and so I have this magnetic field that's clockwise. At point P, I take a line that's tangent to the circle, and that is the vector of the magnetic field. It is down and to the right. So that's the vector for that magnetic field due to the wire on the left. And then here, I let my thumb come out, my finger drop around, so the magnetic field goes in this direction. And so at this point, the magnetic field is down and to the left. So then the resultant is that vector, the green vector. Who asked that? Is that okay now? You understand? There are some others that are more complicated, where you have like 3 wires instead of 2. I will not give you more than 3, though. All right. Yetta? From 23? 13? Okay. 13 from spring 23. Okay, let me erase this. Students have trouble with these. Don't think you're alone. I've had a number of students come to my office. So this is a slightly more complicated one, but the process is still the same. I have 4 wires. These 3 wires generate a magnetic field at this point, where this other wire is. I want to first determine the magnetic field generated by these 3 wires. That's my first step. And I can do the same thing that I did earlier, where I imagine a radial line, then the vector is in that direction. Y'all see what I just did there? My thumb goes into the page, goes around like that, so my magnetic field vector is in that direction. Likewise, I can do this one, radial line. It's going to be in that direction. That's actually going to be a smaller vector, but it's not relevant here. And then here, radial line, it's going to be in that direction. So the net magnetic field is down. That's the net. If I add up those 3 vectors, I get a magnetic field that's down. So now at point A, I have a current that is out of the page and a magnetic field that is down. This is our second step. This is just using the right-hand rule. Current is out of the page, magnetic field is down. That means that this is to the right. The force is in that direction. So C is the right answer. 2 applications of the right-hand rule, but the first one you have to apply 3 times to find out the net magnetic field. Answer? We good? Still processing? Okay. Haley?
Number 12 on 21.
Okay. 12 on 21. Yeah, a number of students have been asking about this too. Y'all are doing good questions. These are questions that a lot of students have had. So here, this is a sketch of a mass spectrometer. When a particle of unknown mass and charge enters into a mass spectrometer, it goes on a circular path. You measure the radius of that path. In this case, I can determine the sign of the charge just by the direction that it's going. Let's label the velocity and the force. The velocity of an object in a circular path will always be tangent to the circle. We learned that last semester. Tangent to the circle. So at that point, it's to the left. The force is always towards the center of the circle. It's a centripetal force. It's center seeking. And then the magnetic field is into the page. So I can determine if these are aligned correctly. Let's see. I like to do V first. V is in that direction. B is in that direction. So with my velocity and magnetic field, my force should be down. But according to this figure, my force is up. That tells me that the charge is what? Negative. So if the charge is negative, that means the force would be opposite what you found. So in this case, it is a negative charge because the force is opposite what you found. Now, let me just show you, you can do this differently. Imagine instead I do it up here. In that case, the velocity is in that direction, the force is in that direction, and the magnetic field is in that direction. And so if we did this one, velocity, magnetic field is into the page, this shows me that the force is up, which is also opposite what we found. So it doesn't matter where you do it on the circle, you'll always get the right answer if you're applying the right-hand rule properly. If I found the force was down, then it would tell you it was a positive particle. The force is what you would expect. Yeah, yeah, of course. Okay, so a number of students have had issue with what is the direction of the force and what is the direction of the velocity in problems like this. So let's just take a moment to address that. So the direction of the velocity, at least initially, is in this direction, right? The particle is traveling to the right, but then some force acts upon it that causes it to move upward. So the direction of the force then is in what direction? It's up. So the velocity is to the right initially, and the force is up. Now in reality, if this is my velocity vector and this is my force vector, what's going to happen as it moves through this path is that both of them are going to change. They're always going to be perpendicular to one another, but both of them are going to change in that circular path. And as it moves forward, the velocity will stay tangent to that line, and the force will remain perpendicular to the velocity. They'll always be like this. The force and the velocity are always perpendicular. They're always orthogonal. So now I want to know what is the direction of the magnetic field. I need to remember too, by the way, that this is a negative particle. That's really important because that means I'm going to take the opposite of my sign, what I find. V is in this direction. F is up. That means that my magnetic field is into the page. But it's a negative particle, so the answer is actually going to be B, out of the page. Okay? Anyway? Good. All right. What else, y'all? Yeah.
You 16.1.
Sure. Okay, definitely going to see one of these. We've done these a number of times. So remember, if I have a 90 degree, those two angles have to add up to 90, and the triangle has to add up to 180. And then also that theta I is equal to theta R. So that means that this angle is 40. If that angle is 40, then that means that this angle is 90 minus 40, or 50 degrees. And that means this angle is 180 minus 90 minus 50, 140, so that's 40 degrees. If that angle is 40 degrees, that means this angle is 50 degrees right here, which means that the reflected angle is also 50. So B is the right answer. And I'll always be asking for the reflected angle off of the second mirror. Okay? Y'all get this one right for sure. All right, because if you've done it once, you can probably do it a gazillion times. It's just your triangles and your angles. Just be careful when you're drawing them. Like I said, I know some of y'all come into an exam and you're kind of stressed and you're a little bit nervous, and I understand rightly so. But just take your time, write down things on the exam. You got it. Like you know a lot more than you think you know about this. Just take your time and write a lot on your exam. Don't do things in your calculator, write them down on the paper first. Students often make mistakes in the calculator. Write them on the paper first, and just, take a big deep breath. Get a good night's sleep tonight. Right? Good night's sleep tonight? Yeah? Good. What's up?
They're gonna likely one similar.
To which one? No, we haven't done any at like 20. There will be some total internal reflection stuff. Well, I mean, let's just take a moment. It's not anything different, but no, I just want to know, if I have this light that's moving through this core, how does the index of refraction here compare to here? Well, for total internal reflection to occur, you have to move from what to what type of index? Low to high or high to low? High to low. So this index has to be higher than this index. So the end of the cladding has to be less than end of the core. High index, low index. This has a high index, and this has a low index. And I told you it's not on there. Let me just make sure. But that you need to know that for the exam about the high and the low index. Yeah, no, there's not. I mean, there are a couple on total internal reflection, but not like that. Okay. Yeah, right. Kyle, and then we'll come back to you, Kaylee.
Can you go through 16?
Yeah, of course. Let's. Can we do a different one? So.
I'm fine with that.
Okay.
Can we do like a little slower though?
I'll try. All right. So, three things that I know. I know that theta I is equal to theta r. I know that if I have 90-degree angle, that these two angles have to add to equal to 90. And if I have a triangle, that those three angles have to add to equal to 180. So, if I have a 50-degree angle here, that means I have a 50-degree angle here. That's just law of reflection. And here I have a 90-degree angle. So that means that this angle is 90 minus 50, which is equal to 40. Right, because 40 plus 50 is 90. And that means that this angle, because I have a triangle right here, it's not a right triangle, but that doesn't matter, it's always 180, is going to be 180 minus 120 minus 40. That's equal to 20 degrees. So this angle right here is 20 degrees. If that angle is 20, that means that this angle is 90 minus 20, which is 70 degrees, which means that this angle is also 70 degrees. Okay? Kaylee? 18 and 21. Okay, so when light passes through the prism, the color that is bent the most is the one with a high or low index of refraction. High index. The bigger the index, the more it's going to bend. So the color that will be bent the most will be the color that's 400 nanometers. That means that it's going to be blue. I don't know why I put orange or green. I don't expect you to know that. Really, I just want you to understand that blue is short wavelength, red is long wavelength. I think y'all know that. Red is right near the infrared. It's the low energy part of the visible spectrum. And then blue is the high energy part of the energy spectrum, of the visible spectrum. That's why UV rays, which are right next to blue, they damage your skin. Right? You get sunburn when you're exposed to ultraviolet because it damages your skin. That's okay? Who's that? Caleb? No. Danny? 16 on 22. Okay, yeah, a number of students have asked this too. So 2 steps to this problem. First, I need to determine what magnetic field has caused this motion. And remember, like we did before, the velocity is in this direction, and the force, what's the direction of the force? To the left. It's towards the center of that circle. The velocity is tangent to the circle, the force is towards the center of the circle. So V is up, F is in that direction. That means that the magnetic field is into the page. So I have a magnetic field. The field that's causing this motion is a field that's into the page. Now I want to know what is the direction of the current that causes that magnetic field. There would be an into the page current on the bottom of the wire, and I know that the magnetic field on the opposite side has to be out of the page. So it's going to be like this and like that. My thumb now gives the direction of the current. It's going to be to the right. As I said, when you're doing these in the exam, it can often be really helpful to just shift your paper around so that it feels like you're all contorted. Just move your paper. I usually just move it so that my index finger is in the same direction as V, and then it's a lot easier to do the right hand rule. Even if your paper is upside down, just make sure that you draw the arrow before you move it back, because if you don't do that, then you're going to draw it the wrong direction. Okay? Yeah. Oh, that was COVID semester, wasn't it? Okay, so this was a ranking, the lowest, from the highest to lowest. So I like to think, are they fast or slow? So as I move from here, it has to travel faster to go in that direction. So this one's slow, and this one's fast. That means that N1 is bigger than N2. I'm going from highest to lowest. So if N1 is bigger than N2, I can get rid of that one. I can get rid of that one. All right. Next, I look at N2 to N3. As I move from N2 to N3, I imagine my wavefronts there. It's going to move slower than it did in medium 2. That means that N3 is bigger than N2. If N3 is bigger than N2, that gets rid of that one. So now I need to distinguish between C and E. I really recommend that you do it that way. Go through and remove options as you determine that they're not correct. That's a great way to approach ranking problems, because sometimes you'll get to a point where you just have one option. You don't really need to complete the problem. But the last step here is to look at the relationship between medium 1 and medium 3. Imagine that medium 2 isn't there. I'm moving here, and then I'm moving like that. That means that when it approaches into medium 3, it's going slow. So that means that N3 is bigger than N1. Let me redraw that just a little bit, just so you can see better, because I was sort of doing that in my head. If I have these light rays, this is N1, this is N3. I've just pushed medium 2 out of the way. It slows down there, so it swings around. So N3 is bigger than N1. That means that C is the right answer. Be careful. Make sure that you are aware of, am I going from highest to lowest or lowest to highest? That's just, read the problem, right? And then be careful as you move through to be clear. Take your time, be deliberate. Am I moving faster or slower? And then also remember that the index is inversely related to the speed. So a slow speed means a high index of refraction. Light travels slower in a high index. Move back into a glass, it slows down. Yeah. 2020. Is this 2020? Yeah, 15. It's 15 on 2020. We're good? Okay. All right. So this is a mass spectrometer problem. I have a speed of 4 meters per second, a magnetic field of 8 Tesla, and a radius of 0.5 meters, and I want to know which particle is it. In order to find this, you have to calculate the mass to charge ratio. R is equal to, I think, mv over qb, if I'm not mistaken. And so solve this for the mass to charge ratio. That's going to be rb over v. rb over v, that's 0.5 times 8 divided by 4. That's 4 over 4, or 1. The only one that has a mass to charge ratio of 1 is that yttrium. Not a real thing, I just made it up. But it's 1 to 1. This will be 2 to 1, 4 to 1, and 16 to 1. Okay? But in your case, you get a ratio of just 1. Okay? What else? Other questions? Y'all feel comfortable with this material? Comfortable? Yeah. Well, I don't know that it's easier. Is it easier than the last test? It is? Good. Okay. That's usually how it works out, but don't take that as a comfort. Like, still be prepared tomorrow. All right. Well, I think that's all. Before you leave, let me just make sure I got your name. So as you walk out, what's 30?